Hello, everyone. My name is Awa. I am one of the co-founders of Anoma. And today I'm here to talk about how Anoma's architecture can enable user-defined markets and applications. So I always like to start with setting up the right framework. And I would like to tell a little bit this evolution of the history behind the evolution of different protocols so far. So I like to think of Bitcoin as like the first generation, which introduced the idea of scriptable settlement. Scriptable settlement, for example, via Bitcoin script, allowed you to, it was really good for building a class of applications particularly. For example, cryptocurrencies with different properties, as well as the other kinds of monetary policies. And what a lot of people don't know, actually, is that with Bitcoin script, you can actually build many other cool applications like color coins, Namecoin, and a bunch of others. And they actually work, right? Vitalik speaks about it in the Ethereum white paper, where he says that he actually mentions these two examples, and then he says that they work, but they become a little bit clunky. They come at trade-offs around usability, and they are restricted properties. So, released in 2015, the deployment of Ethereum marked the beginning of a second generation, a new paradigm of architectures for decentralized applications. I like to refer to it as programmable settlement. Programmable settlement just enables more expressivity at the virtual machine layer, which allows you to build all the applications you could build on Bitcoin with a scriptable settlement, like color coins, as like currently known, the well-established ERC20s, or ENS, the well-established, used to be Namecoin. And a bunch of other cool stuff like decentralized autonomous organizations and new kinds of assets like NFTs, soulbound tokens, and a bunch of other stuff. What you can also build on Ethereum is a bunch of other contemporary, more complex applications. Some examples there are Uniswap, 0x, Gitcoin, CowSwap, a lot of cool stuff, Wyvern, OpenSea, Starknet, Optimism. And yes, they work, but the issue with modern applications that are built only relying on programmable settlement is that they actually they have more requirements that settlement cannot satisfy. And they have particularly two things. One thing is that these protocols are actually application specific. And the other thing is that if you zoom out in the architecture and just forget about what happens in Ethereum, usually that is restricted to settlement. You will see that in the protocol design, they will have at least one component that is centralized or is a Web 2 component. So in the same way you can build color coins in Bitcoin and Ethereum, in Bitcoin, you can build on Ethereum all these modern applications. So what has happened until now? It's been almost 7 years ever since Ethereum was deployed. And there has been many advances in civil resistance mechanisms. We are finally moving away from work to proof of stake, consensus, longest chain consensus in different variants, Tendermint, Avalanche, many others, and scaling architectures. We have sharding, rollups, and many others. But if you look at what it is that the paradigm that they introduce, you will realize that actually every other protocol that has been deployed since Ethereum has been offering programmable settlement, basically the same issues that they offer it in different flavors and colors. So the conclusion is that programmable settlement is sufficient only if you already know which parties are involved and what it is that they're settling on. So for that, programmable settlement is great. But if you look at some of the contemporary cooler applications, you will see that it is not sufficient because one key part of it is that they need counterparty discovery. And this is the case for the vast majority of modern applications. So there's an emergent approach, as you have seen, where you can, if let's say a layer 2 wants to decentralize, they can always do the following, which is they use the Cosmos SDK or Substrate. It makes it easier. And what you do is you build an application-specific sovereign chain, right? It's like a layer 1 that does that specific thing in a decentralized way. And you can actually do this, and it will solve the immediate centralization problem. But the issue is that it comes with actually a lot of trade-offs. For example, the loss of network effects, be it app composability or the software reuse. And in reality, it adds disproportional complexity to the user because the users all of a sudden need to, and the developers too, they all need to reason through these multi-layered security, privacy, and the latency domains, including the token. So another approach would be what we propose, which is introduction of a new generation of applications that is full stack. And this is represented today, Anoma, as a unified architecture that allows you to build full stack decentralized applications. So the architecture of Anoma, in a few sentences, is characterized for being intent-centric. First of all, what is an intent? An intent is, simply put, what the user wants to do, wants to achieve when they decide to interact with a protocol. An intent can be as simple as, I want to transfer, let's say, asset X from A to B, or I want to swap X for Y. Intents in the Anoma protocol are understood as encoding of the user's desired state transition, and they can be anything. It can even be programmatic. Another characteristic is that it is inbuilt natively privacy preserving, and it does it in a very unique way, where there is one unified execution environment able to handle both transparent, shielded, and private states. So an application built on this unified architecture can leverage, in the DApp sense, they can leverage all three different privacy guarantees in one application. The counterparty discovery and solving part is what is really essential. So as I mentioned before, most of the modern dApps require this functionality, and Anoma just offers it from the get-go in a fully decentralized way. And the last part about the architecture is that we're striving for basically enabling atomic multi-chain settlement. This is the idea that at the moment, all interoperability protocols require you that the asset is moved to one security domain before you can use it. So when you do that, you're actually losing atomicity, right? There's always the guarantee that something else happens when that process happens. So really what we're trying to achieve with novel consensus, which is named heterogeneous paxos, is that if a user intent includes an asset, for example, the swap of an asset that lives on Ethereum and another one that lives on a Cosmos chain or whatever other chain, that swap can happen atomically without requiring the user to move them first over a bridge to one security domain. So intent centricity, today we'd like to really focus on the intent centricity of the Anoma architecture. Intents in Anoma are programmatic. They can contain any kind of logic. They can even contain code. And this design philosophy is actually essential to enable decentralized counterparty discovery, which is so essential for interesting applications. And here it has a second order effect, which is it forces or it constitutes a declarative paradigm for building and using decentralized applications. So this diagram tries to explain what a declarative paradigm for dApps means. And this is the state of how we think that applications should be built, where the user only has to worry about creating the intent, describing really what the state transition is that they want and sign it. The intent goes through the Anoma protocol, and the only other thing that the user needs to worry about is whether the intent was settled or not. And this has to be publicly verifiable, right? So in the middle, there is the unified architecture of Anoma. And there's actually a lot of complexity in there. So there's as in complete novel peer-to-peer networking stack, there's decentralized solvers, there's tons of ZKP stuff, there's Fairview, consensus, proof of stake, there's a lot of things that, generally speaking, the user should not worry about. The only thing that the user should worry about is the fact that the intent describes what they want and the protocol, and they don't need to understand at all what happens under the hood. And the protocol is just designed to settle this intent or simply just let it fail. So that is the end goal for applications to be built on Anoma. And this is why it is different to transaction-centric architectures, where they end up being just more imperative, as like users and developers need to reason more around how it actually works in order to use it safely and with high assurance or high privacy guarantees. Whereas in this case, it is declarative, as in, as long as the user defines what they want, then the protocol will do that or not do anything. So I'd like to walk you through just high-level overview of how Anoma is architected, because this is a radically different architecture to what it is that you're used to, especially with scriptable settlement and programmable settlement. So the first part is counterparty discovery. Here I highlighted 4 main, let's say, agents. We have the user that crafts intents via clients, and there is a intent gossip layer that is formed by the intent gossip nodes. Intent gossiping is fully permissionless, and there might never be like a global view of the pool of intents. There might be just sparse. And another critical part of the counterparty discovery layer is solvers. So solvers, you can imagine them to be maybe from the get-go application specific, as like some solvers might just specialize in trying to match intents that are focusing on fungible asset trading, or others that are more focused on NFT trading. But solvers have the incentive to be just monitoring the pool of intents and seeing what it is, which kinds of transactions they can gather together in a way that in combination they satisfy each other. Because intents in Anoma, they are not finalized transactions, they are partial transactions. So here I'm just showing you the flow of how it looks if we have transparent intents, like there's no privacy, just public, just anonymous as the current most layer ones. So the user creates an intent, and then the solvers, the intent is gossiped around the gossip network, and then the solvers find that intent and see that it can be combined with 4 others, and then in combination that forms a valid state transition. There are a few novel primitives that are really need to get like MEV protection from validators from the get-go. Like in this case, the default is that before the transactions go into the mempool, they're all encrypted against Ferial. Then the rest follows the same, but at this point, nobody that is trying to extract MEV by monitoring the mempool can actually do anything, because all they would see are encrypted transactions that were submitted by the solver. The same goes through, later on, the next phases are very standard for proof-of-stake networks that follow some kind of VFT consensus. So here's another unique part, where after the block has been finalized, all the transactions get decrypted at the same time. This is why it cannot be front-run by validators. And here, this is where validated predicates play a role in. Validated predicates are a unique concept to how Anoma architects around accounts and applications. And the key difference is that when validators execute these state transitions, before they can actually finalize on the ledger, they first needs to check all the involved validated predicates that the state transition includes. And only if all the checks are passed, then this transaction is actually written into ledger and actually finalized. And then in the end, the user just needs to verify publicly, just read the data on chain and see if this intent was actually settled. So you can also do applications with intents that are shielded. The distinction between shielded and private, I will tell you in a little bit, but we call it shielded in this case. And the difference between this intent and a transparent intent is that the who of this intent is kept private. So it carries the knowledge proof about this, but the what has to be kept transparent, especially if you want to enable decentralized counterparty discovery and solving. This is necessary because those solvers need to be able to compute over this data in order to find matching intents. Yep, on the rest there are a few nuances around, like right there's the recursive proof, and then at the end, actually at all times the who is kept private. And in the unified execution environment, in this case, in order to verify the proof whether and do the validation of the state, it would just be calling some knowledge circuits. And actually, this is, if you want to leverage zero-knowledge proofs, if you want to leverage auto cryptography, it's different. But if you want to leverage zero-knowledge proofs, this is as private as you can get with an architecture, as long as you want like interactivity, like decentralized contemporary discovery. You can't do better than this with zero-knowledge proofs. So private intents, and here's the difference. The difference between shielded intents and private intents is that private intents are fully encrypted. So even the who and the what, everything around the intent is a ciphertext. And the way this works with this architecture as well is that it leverages really cutting-edge cryptography. It's called fully homomorphic encryption. The intuition around how it works is that you create an intent, you also create an intent, another person creates an intent, and then the fourth person is the one that takes them and does the compute, but at all times the intents are kept fully encrypted. And you might have heard about homomorphic encryption. It is a cryptography that is deployed traditionally in the field of AI, machine learning. But in this case, you could leverage it to like keep applications fully private. Anyways, so that was an overview of the major components. Actually, we are building one instantiation as layer 1 of Anoma for applications that want to benefit with actual vertical integration full stack. But there are multiple deployment models for Anoma. You can deploy it yourself. We call it fractal scaling as a sovereign chain and a community operated chain. So you have all the architecture there, but you get to customize everything around the token, the governance, and your security model as like, do you want it to be proof of stake, proof of work, proof of authority? You decide. You can also deploy it as a layer 1.5. So for example, decentralized L2 constructions. So you could actually, let's say, if Optimism or Arbitrum or Starknet wanted to decentralize the current sequencer, the way they could do this is the counterparty discovery and solving part is just replicated on using the Anoma architecture, and they can still basically function as connect to bridge and then do the final settlement on it, or do the final like market root update on Ethereum. So as a layer 2, you can also just, let's say, with this entire full stack, except for settlement, you can build up dApps while keeping the settlement to Ethereum. There are many applications in the Ethereum ecosystem that want to preserve this property for many reasons. But I would like to stress that actually Anoma is from the get-go interoperable, and it is just not focused on token creation. I would say that over the last 7 years, what is proven is that programmable settlement is actually really good at token creation. So we're not focusing on that. So, okay, enough abstractions. What it is that you can build on Anoma, right? So here are some examples of existing dApps that you can build, but without having to have a one component that is centralized. And one class that is like really well established, there are a lot of applications around this, is different forms of decentralized exchanges. For example, fungible tokens, 0x, CowSwap, for non-fungible tokens, Wire and Seaport, OpenSea, AMMs like Uniswap. You can also build, well, I would say, just for you to imagine it in a more practical way, if OpenSea were to build on this unified architecture, the only thing that the front end, you know how OpenSea relies a lot on counterparty discovery, and they use their website, which is a permissioned, run by the company website. So that is what matches, what allows people that want to sell or buy NFTs to discover each other. That's counterparty discovery. But that is permission at the moment. And then they do a final settlement in the end on Ethereum, but that part, solving the matching part, is done fully by the website. So if OpenSea were to rebuild the entire stack using Anoma, the only thing that the website would do, really, is to visualize the intent gossip layer. So visualize what intents are relevant for NFT trading. And simply, basically, it's going to be an explorer of, in the end, just simply visualize what it has been settled for what's relevant for the users of OpenSea. Another class of really emerging and very trendy applications is rollups, right? Scaling solutions. And you have Optimism, optimistic rollups, for example, Optimism Arbitrum, and Ziggy rollups like Starnet and Ziggy Sync. And if you look in the architecture, you will see that all of them have this thing in common, which is they have one sequencer that is centralized. And a bunch of really cool applications in the Ethereum ecosystem, like I've never seen them anywhere else, like quadratic funding in the case of Gitcoin. So what can you build on Anoma that you cannot build with programmable settlement? So they have the new classes of novel dApps. So you can do, because of a unified execution environment that allows dApps to handle both transparent, private, and shielded state. You can build things like private DAOs, where, for example, parts of it are kept fully private, but there are some parts that are fully transparent, which is something that you would like to have in a DAO. Like votes are kept private, but the results are kept transparent, let's say. You can do also private auctions. These benefits from Fairview as like a major novel primitive that allows you to configure, for example, when there's an auction running, you want to keep this property where all bids are kept private until they are revealed at the same time when the deadline has passed. So, and then this can be combined with, for people who want that, for example, the concealment of the identity, the who is being kept private. A bunch of other things like private games, everything that's multi-party, and then you require some state to be in the process private, it really benefits for an architecture like this one. And one that I want to talk about, which is multi-party, multivariate private bartering. So this is like very loaded as an application, but this is what actually leads to user-defined markets. So remember, this is the goal, right? Of like, this is how applications should be built. And this is what the users should care about and developers should care about, just the creation of the intent and the use, and the verification of the intent. And intents can be anything. So instead of having the constraints of like 0x defining which pairs can be traded, or OpenSea defining like which NFTs, which properties to list, you as a user, you can go nuts here and then go define anything that it is that you want. And this is how you can, maybe the worst case is that it turns out that it's so sparse and then such an obscure thing that it never gets settled, but that doesn't hurt. But the best thing that this can enable is that it turns out there were other intents or counter intents that were actually looking for the same thing or the opposing matching thing. So this is how you could give birth to like user-defined markets. And I would like to actually remind all of us once again about the purpose of this entire space. So suddenly there is a class of problems or design flaws in the space. So some of them are MAV, some of them are surveillance capitalism, and a bunch of other exploitative paradigms that we're carrying over from Web 2. And I think that whenever we think of in a decentralized architecture, whenever we think about that and we try to redesign and build it, we need to think of, can it really enable a more equitable relationship between the user and the system? And if there is room for a few parties to extract disproportionate amount of value, given how little value they give back to the process, then that has to be eliminated. And this is one of the reasons what really motivates me to pursue an intent-centric architecture, because as long as the intent has been described as the user wants, then the system will not add additional information externalities. These are my co-founders. You might know Adrian from early developer Cosmos Fundaments, and also joined Web3 Foundation. You might know Christopher Gose, who is an architect of many primitives that we all leverage today, like the IBC protocol that enables interoperability. You might not know that Christopher Gose built the Wyvern DEX protocol, which powers OpenSea. If you go to ethgasstation.info, check what is the top set of smart contracts called there. And that's me. Well, yeah, Christopher actually has green hair this week, so if you're looking for him to chat with him about architecture, you will only find, you will find him if you find somebody with green hair. And that's it. So Anoma is a unified architecture for full stack decentralization. I would invite you to follow us on Twitter. We just rewritten the white paper. The previous one didn't explain it very well. And if you would like to read it as soon as it comes out, you will be posted on Twitter. Thank you.
Yeah. Do you have any question?
That intent you subscribe to or commit to, is that, are you committing to the state transition, or are you doing assertions on the desired state that it should result in?
The intent? The intent?
Yeah, the intent. Is it on the state transition or the final resulting state?
It's on your individual desired resulting state.
I see. All right.
Is the Feigenbaum testnet still in operation, or have you got a new testnet coming?
So the funny story is that we had actually the network ready with this entire intent system. And we took it down because we realized that people didn't understand really what's going on. And what's cool is that recently we figured out how to actually speak about Anoma. We have been building this system for a year and a half plus. But I think we only recently came to the way of explaining it this way, which I think is more comprehensible, hopefully. And the funny story is that I realized that a lot of applications in Ethereum were all converging towards this architecture. It's just that they were building something that is application specific, whereas we so far are the only ones building a unified architecture that just provides basically 90% of what a dApp needs. But yeah, it's still down, but hopefully comes up later this year. I'm more fully fledged. The new name. It wasn't very popular. I call it after a fractal number. Yeah.
Thank you.